Hello everyone, we will explain about application of Fisher projection for enantiomer determination. Optically active compounds are compounds that can rotate polarized light, which occurs due to the chiral properties of their molecules. Chirality in these compounds is caused by the presence of carbon atoms bonded to 4 different groups, known as chirality centers. Each carbon atom with 4 different groups can play a role in forming 2 opposite enantiomeric forms, which have optically active properties. If a molecule has more than one chiral carbon atom, the number of enantiomer configurations will depend on the number of chirality centers present. For example, in a compound with n chiral carbon atoms, the number of possible enantiomer isomers is 2⁻n. This shows that the more chiral carbon atoms in a compound, the greater the number of possible enantiomer forms that can be formed. Fisher projections are 2-dimensional representations of the 3-dimensional structure of a molecule with chiral atoms, used primarily to describe compounds such as carbohydrates or other compounds with multiple chiral centers. These projections use vertical lines to represent bonds pointing away from the observer and horizontal lines to represent bonds pointing toward the observer.
Diastereomers and their differences from enantiomers. Diastereomers are stereoisomers that have different spatial arrangements but are not mirror images of each other, unlike enantiomers. They usually appear in molecules that contain 2 or more chiral centers, where only some of the R-S configurations are changed. Because they are not mirror images, their physical properties tend to differ, such as boiling point, melting point, solubility, and optical activity. These differences make diastereomers easier to separate than enantiomers. Absolute configuration is determined using the Can-Ingold Krelog (CIP) priority rules, which assign priority to substituents based on atomic number. Groups with higher atomic numbers receive higher priority, while low atomic number groups such as hydrogen receive the lowest priority. After priorities are assigned, the lowest priority group, usually hydrogen, must be placed pointing away from the observer. Then, observe the direction of rotation from priority 1 right pointing arrow 2 right pointing arrow 3. If the rotation is clockwise, the configuration is R. If counterclockwise, the configuration is S. Example, in 3BROMOBUTAN2OL, there are 2 chiral carbons, each bonded to 4 different groups. The first chiral carbon is at C2, where the OH group is attached, while the second chiral carbon is at C3, which carries the bromine atom. Since both carbons have different substituent arrangements, each can have an R or S configuration, meaning this compound can form several stereoisomers. At the C2 chiral center, the attached substituents are O, a carbon bonded to bromine, a methyl group, and hydrogen. According to the CIP priority rules, OH has the highest priority, followed by the carbon attached to bromine, then the methyl group, and finally hydrogen. When the hydrogen is placed pointing backward, the priority sequence 1 right pointing arrow 2 right pointing arrow 3 rotates counterclockwise. Therefore, the C2 chiral center has the S configuration. At the C3 chiral center, the substituents are bromine, a carbon bonded to the O group, a methyl group, and hydrogen. Bromine has the highest atomic number, followed by the carbon attached to O, then methyl, with hydrogen again being the lowest priority. Because the compound has 2 chiral centers, 3BROMOBUTAN2OL can have 4 stereoisomers: 2S, 3R, 2R, 3S, 2R, 3R, and 2S, 3S. The pair 2S, 3R, and 2R, 3S are enantiomers, while 2S, 3R, with either 2S, 3S, or 2R, 3R, are diastereomers. Thank you.